So what we did in section 3, we looked at slope, in other words, the direction of the line, whether it's increasing, that's where the first derivative is positive. We saw where it's decreasing, that's where the first derivative is negative. And we saw the vertex. That's where the first derivative is equal to 0. It's neither increasing nor decreasing. So this will tell you the vertex, whether it's a max or min. Okay, so that gives us the shape, basic shape. But that is only for the vertices. What happens if you think about this? What happens between the two vertices? Let's say I had a vertex here and a vertex there, a vertex there. What if I had that? That's a cubic function. It's odd. The degree is odd, so it goes opposite directions. A is positive, so it's an increasing function. Okay, from here, we can find the x-intercepts. We can find the y-intercept. We can find where the slope is equal to 0, so we can find the vertices. We can determine if it's or where it's increasing, where it's decreasing. But now there's one more thing we have to talk about. This is what's called concavity. Concavity. The shape of the curve. It's either like this or like this. This is concave up. This is concave down. So it opens up, it drops down. All right. On this side, notice on a concavity, like something like this is a quadratic equation. We can see that one side's down, the slope is down, negative, then positive, or positive then negative. What about a cubic function? Well, what is that going to look like? Well, this part here is concave up, but this kind of here is concave down. There's a point somewhere between there where it stops being concave up and starts being concave down, or vice versa. That's where the point where it changes concavity. So it's concave up if the first derivative is increasing. It's concave down if the first derivative is decreasing on the interval. Right, so that's what we're looking at. So a lot of students get concavity, concave with convex. This is just another way of saying concave up. So if something is concave up, that means it's automatically convex. If it's concave down, well, that's what we have to look at. So to talk about concavity, we use the second derivative test. The second derivative simply says this. If the second derivative at some value x is positive on that interval, then f of x is concave up. If the second derivative at some value x is negative on that interval, then the function is concave down. Let's look at this. Oh, we'll also discuss what happens between there. Maybe I'll jump into it here. The point in the middle where it changes concavity from concave down to concave up or vice versa, we call that the point of inflection. The point of inflection is the second derivative where it equals 0. Take the second derivative, set it equals 0, whatever x value, that's where the concavity is going to change. Let's look at some examples here. Example 1. Okay, says find the intervals where f of x for the following one has concavity. Remember, for concavity to exist, you have to have be able to at least take two derivatives. So it's got to be, well, you have a coefficient times x. Well, it is 0, but have to have at least an x squared. So here's A. F of x equals x cubed, and B, f of x equals x squared. Find the concavity. So the first thing we do, got to take the first derivative. Then we got to take the second derivative. For concavity, it's always a second derivative. Set that equal to 0. So it happens at the origin. Because it's a cubic function. That's the one we just had. So if we look at, let's look at x as -1 and x as +1. I plug those in the second derivative. The second derivative is 6x. So it's 6 times -1, 6 times +1. So it's -6. And this one is +6. So this is concave down, like this. This is concave up. So it's like this. So that's concave down, and that's concave up. Let's look at this one. First derivative is 2x. Second derivative is 2. Second derivative is positive for every x. Therefore, it's concave up everywhere. And so all I have to do here is take the second derivative, set it equal to 0, and then look at what happens to both sides of it. Similar to what we did in the first derivative tests. Okay, let's look at example 2. Concavity of y equals 3 plus sine x on 0 to 2 pi. Now they finally give us a domain. First off, find the second derivative. First derivative of 3 is 0. Derivative of sine is cosine. The second derivative of cosine is negative sine. So let's look at, find a point between there. At x equals pi, we get the second derivative equals negative sine pi. That equals 0. Wow, so that doesn't tell us anything. Actually, it does. It tells us that pi is the point of inflection. Remember, if you take the second derivative, set it equal to 0, that gives you the POI. So if we took negative sine x and set it equal to 0, change the signs, so we have sine x equals 0. Take the inverse sine of both sides. So the signs cancel, so x is equal to the inverse sine of 0. What it's asking is what x values make sine 0. So where is sine 0? At 0, pi, and 2 pi. So we know we have a point of inflection. These are the endpoints, they equal 0. So at 0, we have pi. and then 2 pi. That equals 0, that equals 0. So now let's look at what happens here. So second derivative at pi over 2 is negative sine pi over 2. Sine pi over 2 is 1, so it's negative 1. So it's concave down. And then the second derivative at 3 pi over 2, negative sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1. So negative becomes a positive 1. So it's greater than 0. So it's concave up. That's what the graph looks like. Right. Let's look at example 3. Determine concavity and point of inflections, or points of inflection. There you may have more. So f of x equals x cubed minus 2x squared plus 2. First derivative is 3x squared minus 4x. The second derivative is 6x minus 4. Set that equal to 0. So we get 4 equals 6x. 4 over 6 equals x. X equals 2/3. That's my POI. So the point of inflection is at 2/3. What happens to the left of it? From negative infinity to 2/3, and then from 2/3 to positive infinity. So let's look at x equals 0 and x equals 1. Plug in the second derivative. 6x minus 4, 6 times 0 minus 4 is negative 4. So it's concave down. F double prime of 1 is 6 times 1 minus 4. 6 minus 4 is 2. So it's concave up. So the interval is from negative infinity, it's concave down. From 2 over 3 to infinity is concave up. All right. Let's look at example 4. Find the point of inflection of f of x equals x to the 5/3. X to the 5/3, the first derivative, is 5/3 x minus 1, which is 3/3, makes it 2/3. And the second derivative, 5/3 times 2/3, and subtract 1, which is 3/3, makes it negative 1/3. 10/9 x to the power 1/3. It cannot equal 0. It's an asymptote. So to the left of 0, so we're going from negative infinity to 0, and then from 0 to positive infinity. Negative number to the power 1/3 is negative, so it's concave down, and this one's positive, so it's concave up. All right, so this one's going to look like at 0, we have an intercept. So concave down on the left side, concave up on the right. And it's an increasing function. There we go. Example 5. POI of f of x equals x to the 4th. First derivative is 4x cubed. Second derivative is 12x squared. Set it equal to 0. X equals 0. That's the point of inflection. So since the second derivative is equal to 12x squared, and no matter what you put in there, it's always going to be greater than 0. So it's concave up. It's concave up everywhere. Look at example 6. That one's just pretty short. Graph has a point of inflection at the origin because second derivative, yeah. So we have y equals x to the power 1/3. So the first derivative we take is 1/3. Subtract 1, which is 3/3, makes it negative 2/3. And the second derivative is 1/3, negative 2/3, x, subtract 1, is negative 5/3. One over 3 So it's x to the 2/3. Becomes -2/6 x to the 5/3. So my intervals are from in negative infinity, 2 and the 6 can cancel, to -1/3x to the 5/3, -1/3x to the 5/3, comma 1/3x 2/3, and then to infinity. So let's try -1. Let's try 0 here. And let's try 1. It's just x cannot equal 0. What this one could be 2/9. Yeah, so it's 2/9 x to the 5/3. Okay, so at this one, we plug that in there. If -1 to the 5th is -1, so that makes it positive. So it's concave up. We can't use 0, so now we use 1. It's going to stay positive. We got to put it in there, so it's 1/3. It's positive, so it's concave up. Oh no, hold it. All I'm looking at this one, the point of inflection. I'm going from -infinity to -2/9 x to the 5/3, and then -2/9 x to the 5/3 going to infinity. So if x is -1 versus x is 1. If x is -1, it comes positive, so it's concave up. If x is 1, it stays negative, so it's concave down. So it's concave up, going to point of inflection, and then it's concave down. And we know that we know what the graph looks like. All right, let's look at what happens when we have bigger equations. This one is a particle moving Example 7. A particle moving a horizontal coordinate line, positive to the right, is given by the function s of t equals 2t cubed minus 14t squared plus 23t minus 5 for all t greater than equal to 0. It's asking find the velocity, the acceleration, and the motion. So the velocity is simply the first derivative t cubed. So it makes it 6t squared 28t plus 23 and the acceleration, which is the first derivative velocity, which is a second derivative of position. So it's 12t minus 28. See what we can do here. And we'll factor that one. And the bottom one's pretty easy. All right. So the first derivative, find the critical points of the velocity function, which is the first derivative. So 6t squared minus 28t plus 23. So it takes 6t, 6t. Second sign's a plus, they're both the same. They're both the first sign. Now, take the first term and the last term. 6 times 23 equals 138. What times what is 138? When you add them, you get the middle term, 28. We're going to go 2 times 69. 69 is 3 times 23. Six times 8, 6 times 3, 13 is 2 with 1, 18. Use a prime number. One's equal 28. This one. -60 minus 2018. That's what the problem is. It's not 23, it's 22. Six times 22 is 132. So 132 is 2 times 66. So it's made up of 2 times 2 times 3 times 11. So what times what is 132? When you add them, you get 28. Ah, 22 and 6. 22 and 6. So what factors out here is a 2, a 3 plus 11, and a 6 there, t minus 1. And delete the whatever you factored out. Factor 2. So the time for the velocity is 11 over 3 and 1. Those are the vertices. Infinity to 1, 1 to 11 over 3, and then 11 over 3 to infinity. I use 0 here, use 2 there. 7/3 is 3 and 2/3. Let's do 4. So plug in the first derivative. So it's 2 times -11 times -1 makes it 22. Makes it positive, so it's increasing. So it moves to the right. If I put 2 inside there, was it 2, 6 minus 11, 2 minus 1, 2, -5, 1, -10. So it's negative, it's decreasing, it's moving to the left. 2, 12 minus 11, 4 minus 1, 2, 1, 3, 6. So it's positive. It's positive, it's going up, and it's moving to the right. Concavity, I use the acceleration, which is the first derivative of velocity, which is the second derivative of my position function. 12t minus 28. Just solve that. We get t equals 28/12. Makes it 14/6. 7/3. So from -infinity to 7/3, and then from 7/3 to positive infinity. I use 0, and I use 3. At 0, I got -28. At 3, I got 36 plus or minus 28, which is 8. Positive is going up, negative is going down. So it's a min. Oh, yes, it's the only value we have. Take our second derivative, set it equal to 0, solve for t. And we got 7/3. So it's look at the interval from -infinity, 7/3, and 7/3 to infinity. Pick the points, tell me if it's positive. Now the second derivative test for local extrema. It says this under theorem 5. That's what that's called. Suppose the function f is continuous, and then therefore we need the first derivative and the second derivative are continuous. And C is an element in that open interval. At x equals C, if f prime of C equals 0 and f double prime at C is negative, then f has a local maximum at x equals C. So if the first derivative is 0 at C, it's a vertex, and the second derivative says that it's negative, it's concave down. So there's that. It's concave down, so it's a max. If f prime of C equals 0, and the second derivative at C is positive, then f has a local min at x equals C. So first derivative C is a vertex, and it's positive, so it's concave up. Min max. And lastly, if f of C equals 0 and f double prime at C equals 0, the test fails. Or you can't use it to test anything because it couldn't have, it's not necessary, it's not a condition that has to exist. All right, example 8. Let's sketch. F of x equals x to the fourth minus 4x cubed plus 10. Use the following step. Identify where extrema exist. Find intervals where increasing and decreasing find concavity sketch what you can so far. points. Okay, we're going to use that function. Four x cubed minus 12x squared let's find the first true derivative. So it's 12x squared minus 24x. 24x minus 24. Okay, A. The extrema. So at points where the first derivative equals 0. So 12x squared minus 24x. Right, 12x, x minus 2. So set them both equal to 0. X equals that, and x equals 2. Oh, crazy. The original function was x to the fourth minus 4x cubed plus 10. So that's the first derivative. This is the second. I don't need that part. So I have my first derivative, 4x cubed minus 12x squared. Set that equal to 0. So I can take out 4x squared, which is x minus 3. So x equals 0 and x equals 3. So for this information, let's look at our intervals. Negative infinity to 0, 0 to 3, and 3 to infinity. Negative 1, 1, and 4. Let's put that in the first derivative. Is 4x cubed minus 12x squared. 4 negative 1 cubed minus 12 negative 1 squared. 4 cubed, 12 1 squared. 4 cubed, 12, 4 squared. Let's see this. 4 times -1 minus 12. -4 minus 12 is -16, so it's decreasing. 1 cubed, so it's 4 times 1 minus 12 times 1, so it's 4 minus 12 makes it -8. It's also decreasing. So no extrema at x equals 0, because it's always going down. 4 times 64 minus 12 times 16, 256 minus 72. It's positive, so it's going up. So min at x equals 3. Oops. All right, that's A. Now we're going to do B. Intervals where it's increasing, decreasing. And we just did that. From -infinity to 0, it's decreasing. From 0 to 3, it's decreasing. 3 to is increasing. Let's see. Find where the graph is concave up, concave down. So for this, we have to use a second derivative. 12x squared minus 24x. 12x squared minus 24x. We could take out 12x, which leaves us x minus 2. So x equals 0 and x equals 2. So now we should determine if they're concave up, concave down. From -infinity to 0. From 0 to 2. 2 to infinity. So we have -1, we have 1, and we have 3. Plug those into second derivative. 12 times -1, -1 minus 2. 12 times 1, 1 minus 2. 12 times 3, 3 minus 2. -12 times -3 is positive 36. So it's positive, concave up. 12 times -1 is -12. It's negative, so it's concave down. And at 3, we have 36 times 1, which is 36. It's positive, so it's up. So it's concave up from here to here, concave down, and concave up again. Next question, next part. Sketch the general shape and plot some points. Function x to the fourth minus 4x cubed plus 10. So I know at 10, I have an intercept. I know that my leading coefficient is 1, so it's greater than 0, and my degree is 4, even. So both ends point the same direction. Concave, they're both up. So I know for whatever reason that the ends of the graphs will go up. From the extreme, the outside x-intercepts. Okay, now where do we have our first derivative? Set it equals 0 at 3. So this, with the only x-intercept we have, I mean the intercept, the minute we have is the 3. So it's got to cross the x-axis, but it also has to cross through there. Something like that. Let's see. What is that? That was example 9. What? 8. Let me look for example 9. Oh, there's example 9. And so 9. Oh, let me see if I get these pens to work. Hold on. So example 9 says sketch this function. We have x plus 1 squared over 1 plus x squared. The bottom can never be 0 because that's always a positive number. So there are no asymptotes. The x-intercept is at x equals -1. Now we're going to do the derivatives. Oh, no. Let me see how many examples I have here. Because my pens are not working. Now we got 2 more after this. I'll try to muscle through this. x equals 1. So now we have to find the first derivative. So that's x plus 1 squared, 1 plus x squared. This is f and g, f prime, g prime. So 2x plus 1, 2x. So first derivative is equal to 1 plus x squared times 2x plus 1 plus 2x x plus 1 squared. But minus, since it's a quotient. And that means it's over the bottom number squared. Okay. X plus 1. So I can take out a 1 plus x squared. The bottom. Now factor it out 1 plus x squared. So it leaves me with 2x plus 1 minus 2x. 2x times x plus 1. That's an x plus 1 squared. That's squared. So now I can take out, they both have a 2, and they both have an x plus 1. So I could take out a 2x plus 1. So that's that, and one of those. So then I have a 1 plus x squared minus x minus 1. X plus 1, 1 plus x squared minus x plus 1. Two x plus 1 x squared minus x plus 2. That one can be factored out as x. Ooh, no. So we have 1 plus x, 2x plus 1. That's one equation. Minus 2x, x plus 1 squared. So I have these two terms. I have an x plus 1 and a 2 I can take out, which leaves 1 plus x squared minus x plus 1. No, it's minus. That should be x plus 1, but distribution becomes a minus. So the ones cancel. So we have x squared minus x. It becomes x times x minus 1. X there. It's x squared minus x. X squared cancels. So it's a 1 minus x left in there. 1 minus x. X plus 1. 1 minus x over 1 plus x squared squared. It's x minus x squared plus 1 minus x with 1 minus x squared. I just took these two and multiplied them out. That's my first derivative. I gotta repeat the whole process to do the second derivative. 1 minus x squared over 1 plus x squared squared. 1 minus x squared, 1 plus x squared squared. So this one's going to be negative 4x equals 4x 1 plus x squared. So the second derivative is going to be negative 4x times 1 plus x squared squared minus 2, 1 minus x squared, 4x, 1 plus x squared, all over 1 plus x squared to the fourth. Because it was squared, we squared it again. Oh, we put squared, squared. Squared. We have negative 4x, 1 plus x squared, squared. Two times 4x is 8x. 1 minus x squared, 1 plus x squared. So out of both of these terms, they both have a negative. They both have a 4x, 1 plus x squared. 1 plus x squared plus 1 minus x squared. One plus x squared to the fourth. So one of these can cancel with one of these. Negative 4x. I could drop the parentheses. 1 plus x squared plus 1 minus x squared. One plus x squared to the third. The x squares cancel. We'll take out negative. No, I got the 1 plus x squared. One of these are gone, that one's gone. 2. I forgot the 2 right there. So it's 2 minus, so this one becomes 2 minus 2x squared, which leaves us with negative 4x. 1 plus 2 is 3. Negative 2x squared plus 1 is negative x squared. 1 plus x squared to the third. That's the second derivative. Right. So we have the first derivative is 2 times 1 minus x squared. Oh, come on, no times. 1 minus x squared over 1 plus x squared squared. The second derivative is negative 4x 3 minus x squared 1 plus x squared cubed. So the critical points. That's what we have. That's my first derivative, that's second derivative. Critical points is where it equals 0. So I take the top, set it equals 0. 1 minus x squared equals 0. X squared equals 1. So x is equal to plus or minus 1. Those are my critical points. Now this one, second derivative, the points of inflection. Gotta find the max or min for these. So the bottom can never be 0, so that's good. Bottom can never be 0, but it can't be negative in this case. So I'm going from negative infinity to negative 1 to 1 to infinity. So if I put negative 2 in there, 25 on the bottom, negative on top. So at this interval, at negative 2, that's positive on the bottom. It's 4, it's negative, so it's decreasing. At the next interval, from 1, negative 1, put 0. So it's positive, it's 2, so it's increasing, so it's min. And then from 1 positive infinity, I put 2. So 1 minus 4 is the same thing as this one, so it's negative, it's decreasing. So we have a max here. A min at -1, a max at 1. So now we have here bottom cannot be 0, so there's no asymptotes. A minus x squared said equal to 0. So x equals plus or minus square root of 3 for the point of inflection. There's two of them. There's a point of inflection at negative radical 3, and there's a point of inflection at positive radical 3. Now I gotta find concavity. So I'm right for this one. So from negative infinity to negative radical 3 to radical 3 to positive infinity. So we have these three. So it's -2, 0, 2. So 3 minus 4 is -1. That makes it positive. Makes it a negative. So it's a negative. So it's concave down. It's 0. It's 0. So 0 is a point of inflection. And at 2, -8, -1, it's positive. So it's positive, it's concave up. Looks like something like that. Zero. It's not a point of inflection. There, I don't have to worry about it. Okay. Example 10. And we'll call it as grade. Sketch the graph. F of x equals x squared plus 4 over 2x. So we know x cannot be used. It's an asymptote. And then x squared plus 4 equals 0. X squared equals -4. X is plus or minus 2i, so no x-intercepts. The first derivative. X squared plus 4 over 2x. 2x over 2. Two x times 2x minus 2x squared plus 4. 4x squared minus 2x squared minus 8 over 2x squared. Makes it 2x squared minus 8. Zero is still the asymptote. So my critical points, 2x to the 4th minus 8 equals 0, 2x squared, not to the 4th, squared equals 8, x squared equals 4 divided by 2, x equals plus or minus 2. So if we take negative 3, 0, 3. Put them in my first derivative. The bottom can never be 0. The top can be, so it's 2 cubed squared. Negative 3, so it's negative 3 squared is 9. 2 times 9 is 18. 18 minus 8 is 10. 9 over 18, so it's 5 over 9, it's positive. So it's increasing. Undefined. It's positive. All right. Well, I guess I could also, there's a 2, so I can factor out a 2. X squared minus 4 over 2x squared. Squared. Oh, no, squared. So it's 4x, x to the 4th. So first derivative is x squared minus 4 over 2x squared. So it's always, it's consistently increasing. So my second derivative squared minus 4, 2x squared, 4x, 2x. Two x squared minus 4x, x squared minus 4. All over 2x squared squared. This is 4x to the fourth. Cubed minus 4x cubed plus 16x. These cancel. 16x over 4x to the fourth. The fourths cancel. 1x cancels, so we get 4 over x cubed. So it has no point of inflection. It cannot equal 0. So it has no point of inflection. Since we have 0 of our asymptote, let's see what happens to both sides. When x is negative, it's negative, so it's down. If it's positive, so it's up. Okay, so looking at the original equation, so the degree of the numerator is bigger than the bottom by 1. X squared plus 4 over 2x. If I do long division, because we're going to have a slant asymptote, oblique asymptote. So what times 2x gives me x squared? 1/2 x. Subtract. So the graph is going through the origin, up 1 over 2, up 1 over 2. So the only way it could be is if it's concave up. Because if it was the other way, it's concave down, concave up. So on the left-hand side, it's concave up, right side concave up. There's the graph. Okay, everybody. That's it for that one. Sorry it took so long. That one did take a long time. But we're done with the basic graphing and shape design of these things. So the next section we're going to cover is look at not rational functions. We're going to look at applied optimization. These are pretty all going to be word problems, but we're going to see how they apply to the real world. And then we'll finish up the chapter on what's called Newton's method, which is an iterative process. Is if you have a problem, you don't know what is supposed to be the answer to it. So you just start with a best guess and keep on putting it in there until it pretty much solves itself. That's what we call an iterative process. It just keeps on repeating the process until it gets a good answer. Everybody, I will see you guys.